you so much, Chris, and thank you for the conveners and everyone here for having me. So one of the central pillars of astrobiology is determining the distribution of life in the universe. And so I'm just going to start my talk with the modest observation that most of the universe is outside the solar system. And so we have a really, actually very difficult question, though, is how would we recognize life on a distant exoplanet? So this is an image of the Earth, that's that pale blue dot on the lower right from the Cassini spacecraft. And Saturn is 10 AU away from the sun, or 10 times the distance between the Earth and the sun. Proxima Centauri, the nearest star, is 4.2 light years away, which is 40 trillion kilometers away. And that's the closest possible potentially habitable planet in the universe. And so that's an incredible challenge, because a planet that we're used to seeing as a verdant blue dot, or sorry, a verdant blue marble with clouds and vegetation and continents and ocean is going to be reduced to a point spread function on a CCD. And so it's an incredible challenge to then say, how can we determine whether there are living processes on that planet? In 2016, in the summer, the Nexus for Exoplanet System Science convened a team of astrobiologists to sort of compile all of the current knowledge on remotely detectable biosignatures. And these are some of the fundamental questions that need to be answered. What does life produce? And accordingly, what are the signatures of those products of life? Can abiotic processes fool us? Are there geochemical or photochemical processes that would mimic the kind of remote signatures we would expect from a planetary biosphere? How do we determine the presence of life given limited data, given that point spread function on a CCD? And how do we quantify our uncertainties? Is there a way in which we actually survey dozens and dozens of planets and statistically infer the presence of life, even though we can't say definitively it's on one planet or another? So these are really, really tough questions, and they have a lot of input that's necessary from a wide variety of scientists: geologists, geochemists, biologists, astronomers, data scientists, and engineers who will actually determine what's possible in terms of signal-to-noise ratio and the types of gases we can detect, and the lower limit on the abundance of those gases that we can detect. And so one point I want to make really clearly is that we're not looking for life on exoplanets. We're looking for planetary biospheres. There needs to be a robust exchange of gases from the ocean and the surface produced by life. That signature needs to be global in extent. The products of life need to produce observable features: line absorption, vapor rotational transitions, dissociation cross sections. They need to build up to detectable amounts, so they need to be robust to photochemistry that may change from star to star, and they need to be separable from abiotic processes that may otherwise fool you into thinking that this product is produced by life. And so there are kind of two ways of looking at this. There are Earth-based approaches, which is more top-down. And Earth-based approaches, for example, is looking at the modern Earth and noticing that we have oxygen and high chemical disequilibrium in our atmosphere. And so you automatically pass many of these tests for global planetary biosignatures. There's a heritage of existing data. We'll always have more information about the Earth. And we can leverage really rich geochemical archives about the changing chemical composition of our atmosphere. The limitations are that we're limited by the environment, by the fact that the Earth has a certain composition, that it's not universal, and also that there's historical contingencies, evolutionary contingencies in the evolution of metabolisms on Earth. So the other way of looking at this is sort of an agnostic or ground-up approach. So looking at generalized models for thermodynamic equilibrium, looking at all the molecules that could be produced by life, and then going and being very careful about thinking about what their ability to build up an atmosphere would be and what their observable signatures would be. And you're not constrained necessarily by Earth history that way. You have a broader universe of potential signatures, but there's a lot of modeling work that needs to be done to advance that. So I wanted to show this graphic. Dave mentioned a biosignature as a substance, object, or pattern whose origin specifically requires a biological agent. And I left out process there, which is really important, because when we're looking at exoplanet biosignatures, we'd be looking at a spectral feature. We're inferring the presence of a gas based on that feature or surface signature. And then we're inferring further a process that created that. And so one really important example is oxygenic photosynthesis, which uses really available cosmically abundant substrates, water and carbon dioxide and light, to create organic matter and oxygen. That oxygen produces a spectrally observable signature, and it's further processed in the atmosphere to ozone, which also produces its own signature. There are other types of biosignatures that depend on the kind of observation mode we may have. So surface signatures, one example that's been discussed a lot is the vegetation red edge, which is the difference between effectively chlorophyll absorption in the optical and the intracellular scattering by vegetation in the infrared, and it creates incredible jump in the reflectance of leaves and other photosynthetic organisms. It can be observed by space. It's used to map vegetation on Earth, and if it an analog were present on exoplanets to significant coverage, it would also be a remote signature. And then either those gases or surface signatures may change as a function of time, and that may give you additional information. So there are many different gases and surface signatures that have been discussed. Importantly, not all of them will be observable for every inhabited exoplanet. Even our own planet has limitations in this respect. So this is an Earthshine spectrum of Earth. It's obtained from reflected light from the moon, reflected back to the Earth, and it sort of represents a disk average spectrum of the Earth. And from this spectrum, from the interaction of the molecules in the atmosphere and from the reflectance of the surface, and then the transmission out to remote observer, reflection out to remote observer, we can infer the presence of water vapor in our atmosphere, a sign of habitability. The blueness of the sky tells us about our atmospheric mass. The vegetation jump is present in the near infrared, signatures from oxygen and ozone. There are small signatures in this reflected light spectrum from methane and carbon dioxide, but they're sort of small. And that's because we have low abundances of those gases in the modern atmosphere. Wasn't necessarily always the case. So one way of expanding our template of potential biosignatures is to look at Earth history. So Earth has gone through titanic shifts in its chemical composition, both in the atmosphere and the oceans. For half of Earth history, there was no oxygen in the atmosphere. And for a substantial part of Earth history, 40% of Earth history, oxygen was present, but it may have been much, much lower than today. So if you were to travel back in time, for most of Earth history, you couldn't breathe the atmosphere. But that has an incredible impact on the remote signatures of that planet if you were a remote observer. So in the Archean, you could infer the high presence of methane, but you would have no detectable oxygen. In the Proterozoic, you may see ozone, but not oxygen. Whereas today, oxygen and ozone are very detectable, but in our reflected light spectrum, methane has a weak signature. But this shows the importance of Earth's geochemical archive in informing the potential remote signatures of exoplanets, because we will all have that geochemical archive for the Earth and not for any exoplanet. So this is a simulation by Jada Arney characterizing an anoxic potential biosphere. So we're early in Earth history, and we're looking at an Archean type Earth with high methane and high CO2, and the methane bands are much stronger than they are on the modern Earth. And if the methane to CO2 ratio exceeded a certain value, we would actually have a hydrocarbon haze, similar to that on Titan, which would have its own UV signature. If we look in the middle Earth history, in the Proterozoic aeon, as I said, oxygen is probably much lower, perhaps as low as 0.1% of present atmospheric level. If that were true, then the oxygen A band, the most remotely detectable signature of oxygen in our atmosphere, would not be detectable by a future space-based telescope. But ozone would be. Ozone absorbs in the ultraviolet. There are unique technical challenges in looking at the ultraviolet and the near-infrared where water would absorb. And so this is sort of an example of Earth history and our extrapolation for Earth history informing the technical requirements on the search for life elsewhere. There are other approaches, as I said, pioneered by Sarah Seeger's group, including William Baines, which is to look again, instead of from the top-down approach, from the bottom-up approach. And think about all of the molecules that could be produced by life, whether they're stable in an atmosphere, what biomass is required for them to build up to detectable abundances. and whether they would have geophysical false positives. And you can group existing biosignatures in this way, and you can also potentially uncover new ones, and then have a motivation to go measure their laboratory spectra and put them in your photochemical models, et cetera. And so this is also an important perspective on the frontiers of exoplanet biosignature science. I want to really make clear a point, which is that photochemistry and stellar context is going to be really, really important for characterizing potential remote biosignatures. Okay, and so the UV spectrum of stars can change by orders of magnitude depending on the temperature and the activity of that star, and the ultraviolet radiation is what drives the photochemistry. And so one example of this is if you took Earth and you, instead of kept the atmospheric composition constant, you kept the boundary conditions constant and changed the star and put it around an M-type star, which was representative of 70% of the stars in the galaxy, then your methane abundance would be 1,000 times higher. And that could have an incredible consequence for remotely detectable signatures, both in transmission spectroscopy and in reflected light spectroscopy. So self-consistent photochemical models are also incredibly important considerations. I mentioned abiotic processes. So there have been many independent groups from a variety of disciplines and research groups and backgrounds who have put forward potential ways that you could make, for example, oxygen and atmosphere abiotically, either through photolysis or through rapid escape of hydrogen. It depends on the evolutionary history of the host star. Not everyone thinks that these mechanisms are possible. Importantly, though, we can predict the spectral implications of those processes. So if you generate your abiotic oxygen through the photolysis of carbon dioxide, then you would expect no methane and high abundances of carbon monoxide. And so we can use the predictions from these models to sort of inform the technical requirements for discriminating against these false positive scenarios. There's also advances in chemical disequilibrium. So this is just a really quick plug for work by Josh Christiansen-Totten, who's looked both at modern Earth and Archean Earth and looked at the Gibbs free energy of the system and how that relates to potential biosignatures. So everyone is familiar with the oxygen-methane chemical disequilibrium couple. By free energy, that's not actually the largest. It's the coexistence of nitrogen, oxygen, and liquid water in our atmosphere. So these calculations can be done, and they imply that if we, for a modern type Earth, saw nitrogen, oxygen, and liquid water, that there would be a strong biosignature. Methane, carbon dioxide, and water are also strong biosignatures for that reason. And so I'll end with this sort of hope, this comprehensive model put forward by David Catling and advanced also by Sarah Walker in this series of review papers sponsored by Nexus, which is that we can combine all of this information, the context of the stellar system, the data that we retrieve, the forward models that can incorporate self-consistently photochemistry, and we can put that all together and get a statistical likelihood of whether that planet has a compelling biosignature or not. And that is iterative based on not just the advances of our models, but the continued observations that we will receive in the future. And so I'll end with just a summary of those Nexus review papers and other review papers by prominent people in the field, including Sarah Seeger and Lisa Kaltenegger, who have their own perspectives on exoplanet biosignatures. Thank you.